next lesson. We recording? We are. Okay, this is the next lesson then. Got that? Oh, no, we do not, of course. There it is. Just before I start the new lesson, can you tell me where you are with the lab report? So, Amanda, how far are you away?
I did now, so I did to the procedure.
What have you typed? Typed?
Nothing.
Okay, thank you.
No, because everything I'm typed after.
Oh, okay. Sohi, how far are you? Okay, so you've typed anything? No, okay. How far are you?
No calculation.
What have you typed?
Introduction and diagram for electricity and
Okay.
I finished last program. I finished home school.
You finished the electricity and Newton?
I didn't turn it.
Didn't turn it, okay.
I will check my electricity library.
Okay. So what were you doing during the break then? Having a nice time? Yes, okay. Right, our next class is Thursday. Can you bring what you did on Thursday? I want to give you some feedback. Thursday. Today's Tuesday. Yes?
Can I say I will turn to you?
You can show me what you have later, yeah? That's fine, yeah. Okay, induction. Have you got that? Yeah? Okay. So we have seen that a moving charge in a magnetic field will experience a force. That's using the left-hand rule, remember? So this is the magnetic field. This is where the charge is moving, and this is the force it feels. Remember this before the holiday?
I should write that down.
Please, yes, you should, yeah. Force, magnet, current. Remember this?
No, I remember.
Good, okay. So, what happens if we move the magnetic field? So in the picture below, what we have is a magnet, and we're moving the magnet around this conductor. And what you notice will happen is that you get a current here, voltage, So in other words, when we move the magnet, we can make a current when we move the magnet. So this is called electromagnetic induction, when we move a magnet to make a current. So you don't need to write all this down, but I think the picture might be good with the title, electromagnetic induction. So if you can try and draw this in your notes. You understand what's happening in the picture? So you've got like a magnet, and you're moving the magnet, and then there's a wire around the rod, and here you can see on the voltmeter there's a voltage only when you move the magnet, but if you stop, then no more voltage then. So while the magnet is moving around it, it can make a voltage. This is called induction. This is what induction means. to make a voltage by moving a magnet? Oh, it can be anything, just some copper pipe or something. It's not important. The wire is what's important. In fact, you don't really need the pipe. You can just have the wire like this and put it in and out of the wire. Okay, did you draw that? Yes? Continue? Sorry, yeah?
She also remembered this. How to do this?
I don't think it's too difficult to remember. Yeah. The voltage is moving as you move the magnet. Yeah. Okay. Continue? Yes. So, while the magnetic field is moving, a voltage will show. Okay. So, the definition is electromagnetic induction is the production of an electromotive force, a voltage, across a conductor exposed to a change in magnetic field. So, this is the definition in words. I'm sure you prefer the definition in pictures. Yeah. Continue? Yeah? Okay. So that is, induction means producing a current, that should say by changing the magnetic field around the conductor. And we have two laws for it. Let me just fix that. Right. Okay. Right, so here are two laws for induction. The first one is called Lenz's law, and it says if an induced current flows, its direction is always such that it will oppose the change which produced it. So there's a picture here. Before you write it down, let me try and explain the picture. So what happens here, as you move the magnetic field in here, the current that's made will try to go backwards, opposite to the magnetic field's change. So the magnetic field goes in, so the current will try and go to the left. So it will come out here, go down, and go this way. Okay, so you can see the current here. It's moving opposite. It wants to go this way as the magnet goes in. And when you pull the magnet out, the current will want to go that way. So it comes out here. Okay, so this is called Lenz's law. Try to draw this. Now you don't have to draw it as nice as this, but I want to see that when the magnet goes this way, the current wants to go that way and will come out here and go down.
Which hand are you to?
No hand. It's which way the magnet is moving. So for example, it's like
But
if
it's usually
no, it's if you put the magnet in this way, the current will come out to the left. For example, if I put the magnet in here, the current will come out here. If I pull the magnet out this way, the current will want to come out the other way. That the current will want to move opposite to the magnet. So if the magnet goes in here, if the magnet goes in on the left, the current will want to leave on the left. If the magnet comes out of the left, the current will want to go in on the left. This is Lenz's law, that the current will want to move opposite to the magnet. What happened? Okay, ready?
No.
No. Yes, no? No.
What force coil
The coil repels the magnet.
to L?
Yes. Don't draw it too beautiful, please.
No, ugly.
Ugly is gorgeous. Yes? Ah, not too ugly. Okay. Okay. Next now. So I said there are two laws. Come on. Here we go. So far we know that a moving magnetic field will cause a current to flow. That's great. And we know the direction. But we don't know how to calculate the voltage. So in the picture at the start, if I go back to it. Alright. So we know if we move the magnet to the right, which way will the current move? To the left. So we get a voltage here. So the voltage will show. But what we don't know is how much voltage. We just know there will be a voltage. Lenz's law tells us which way the voltage will move, the current will move, but Faraday's law is what tells us how much we have. Faraday's law says that the voltage is equal to this formula here. don't worry too much about the minus. The minus is to remind us that it will be opposite to the change in the magnet. Yes?
So we should add another.
You don't have to, it's okay. Continue? Yeah? Yeah? Okay. So I'll show you how to use this formula. The minus is in fact Lenz's law. I'll show you how to use this formula in a little bit. So, if we move a magnetic field around a conductor, or the conductor moves around the field, then can we use this to make power? And the answer is yes. So we have here the AC generator. So here's the picture of the AC generator. So look, what you have here, north and south, and then you turn this wheel. So as you turn this wheel, it's like you're moving the magnet around the wire. I'll give you an example. So imagine this is the wire and this is the magnet. If you move this, what happens here? You get current. Yes? Now can you see that doing this is the same as doing this? That really, it's still like the magnet is moving, except it's easier to move this. Yeah? That's what you have here. By moving the wheel, it's like you're moving the magnet around the wheel. So we have a current that runs now along here. It's almost like the motor. Remember the motor we did before the holiday? But there is a small difference with the wheels here. This one is connected to this ring, and this one is connected to this ring, and it goes through it, but doesn't touch here. So this one is always touching this side, and this one here is always touching this side. That's really the only difference. And then what you get here is a current. So here maybe you can put like a light bulb or something. And this is how people make electricity. Like at the, I don't know, I'm sure you have it in China as well. You know, at the waterfall, the water comes down and it turns the big wheels. And these make the electricity for the homes. Or the wind farm. The wind blows, it turns it around, it turns this and it makes electricity. So actually this is how you make electricity. Yeah? Get the idea for this? So you will need to draw this.
Use the force to turn the...
Use a force to turn the conductor, yeah. And then as you turn it, there will be a current in the conductor.
Turn what?
Turn this part, the wheel. You turn the wheel. And this here turns around. Like here, it's like, this here is like this. So you turn the wheel and this goes around. And as it moves around, you get a current here.
What can you say the current will go here? You know that
It's difficult.
I
It's too difficult for me to imagine because no, I can't imagine it.
Yeah.
Because in the example with Lenz's law was simple. The magnet and the conductor were moving like this. Here, it's more complicated, yes.
the middle to extend middle
No, but I have a picture that will help you with the direction in a moment. Yeah.
What is the meaning of behold?
Of the what?
Behold is
Oh, it's just me being silly. This is called an AC generator.
bigger?
Possibly. Let me see. Anyways, just before you draw the picture, we have the formula V equals minus N, change in the magnetic flux over the change in the time. But remember that the flux is equal to BA, and let's ignore the minus N for a moment. So how does the BA change? Well, the normal to the plane which is rotating makes an angle theta with the field. So if you remember from the first lesson, well, it wasn't the first lesson, we need to add in a cos theta to the BA. So we have this BA cos theta. Anyways, the BA is constant, so we really just need to know how the cos changes, but the derivative of cos is sine. So after all of this explanation, I'll try and explain it on some paper as well, we can get an idea of what the current looks like. You have, I'll show you the picture in a moment, the voltage is equal to the change in the magnetic, I know there's a minus N here as well, but I'm going to just forget about it for the moment, over the change in time. That's equal to the change in BA cos theta over change in time. But the area is constant and the magnet is constant. The only thing that's changing is the angle. So this equals BA, the change in cos theta over t. And this here is a sine. You know this from derivatives, that the way cos changes is by a sine. So after all of this, I just want to show you this graph. That if this is the time, and this is the voltage, the graph looks like this. Yeah, this is the formula. This is equal to BA cos theta when the magnetic field and the conductor are not perpendicular because it's turning, you know. So the graph you get is this sine shape of graph. So the voltage goes up and it goes down and it goes up and it goes down. Sometimes it's positive and sometimes it's negative. So when it's like this, the current is going this way. But when it flips over, then the current is going the other way. So it keeps changing its direction every time it turns around. And you can kind of see this in the graph as well. We'll talk more about this, but I know you want to draw this, so let me just make the picture bigger.
Cos theta over t sine theta?
Kind of. You know that the derivative of cos x dx, that's equal to minus sine. Yeah. So when I write the change in cos theta over dt, well, this theta is changing, so really it's kind of like cos omega t over t. It's a bit like derivative of cos omega t over dt. It's not part of physics course, so you don't need to worry about this, but I just wanted to give you a reason why the graph looks like a sine. And the reason the graph looks like a sine is because in the formula here there's a cos, and we want the change in the cos. But it's not part of the physics course. I just thought you might want to know why this looks like a sine graph. And the reason is because originally there was a cos here. But anyways, that's more than what you need. Let me give you the picture here. Can you see? Yeah. Andy, to try and answer your question earlier,
Yeah.
when this moves up to the right,
Yeah.
it's like the magnet, the north moves down on the left. You know, if I turn this way, it's the same as if I keep this still and move the magnet down this way. So it's like the magnet is going to the right, which means the current wants to go to the left, you know. Andy asked me a question earlier, how can we know which way this is moving? And it's hard because it's spinning. But if you think about it like this rotating to the right is the same as it not rotating, but the magnet moving to the left. So the magnet wants to go under. So it's going this way, so the current would like to go backwards, opposite. So the current wants to, oh, no, that's wrong.
Two change.
No. Well, I hope the picture's right.
Yeah.
No, sorry, Andy, haven't a clue. Okay, sorry. Continue. Continue? No. Sometimes they ask us to draw this in the exam. And the other one, the motor.
If I draw the teacher, the slip ring, should I draw two or?
Oh, two, of course. Did you draw one?
No.
Okay.
It's different.
I know.
Then we should put the name.
Of course.
Gosh.
Yes.
The slip ring, like two.
They're not touching.
Touching?
Not touching. Uh-oh.
The half ring. There are two rings.
Two rings, yeah? Yeah.
What is the green line?
Green line? Oh.
What's the blue and gold?
Here?
Yeah.
Oh, that's just the connection between here and the slip ring. And it's always touching this as it goes around. And then there's a connection between here and this ring, and it's always touching here as it spins around. So you have the two rings, and these are always spinning around. Yeah. Yes, use your imagination.
When you spin around, the
Mhm.
green line didn't come.
No. because this and this spin together like this. Look, they move around together. There's no
Oh, yeah, I use my imagination.
Good, okay. Good. Imagination is useful for physics. Okay, continue now. No, you're taking a picture? This, great. Okay. Now, usually, if, in the picture, I know it looks like it's flat like this at the start, but usually the machine, we have it like this at the start. Okay, so this part. Usually at the beginning it's like this, and then the magnet, we keep the machine in this position at the start, not this position. It doesn't matter. Just for the picture here, it starts off in this position. This is the graph I drew earlier for you. It starts like this, and then when it turns, this is when you have most voltage. But then when it turns, you get most voltage. But then when it turns again, that's hard. Okay, start like this. Then it turns 90, most voltage. Then it turns again, no voltage. Then it turns, where am I? Again here. Oh, so hard.
In the same direction.
Yeah, turn in the same direction. Every time it's vertical, you have no voltage. Every time it's horizontal, you have most voltage. I think the reason they keep the machine like this at the start is because then there's no voltage at the start. So maybe it's safer. Actually, here, this would be better. Look. Okay, so at the beginning it's like this, and this is the top. No voltage, maximum voltage, no voltage, and then minimum voltage, negative number, and then back to no voltage, zero voltage. Yeah. It's a sine. Actually, this is a sine graph here. You get positive and negative voltage because the current keeps changing its direction every 180 degrees.
Like a maximum voltage is that when the blue line goes to the S, then it is maximum.
When it's horizontal, yeah.
The blue line goes to the S and red line goes to the N. The time is maximum. Blue line goes to blue and red line goes to
I suppose, I never think about it like this. Maximum would be, I guess so, yeah. Don't worry about that.
Yeah.
But in the exam, sometimes they ask you to draw this picture with the position underneath the picture to show you when is maximum, when is minimum. So I've seen them ask you to draw this in the exam, the position and the voltage. Voltage, no voltage, yes. Yeah? Voltage, no voltage. I guess it does matter for positive or negative. So this one here, the right, well, no, I suppose so. It only matters for the direction, if it's positive or negative. That's all that matters. In the exam, for the picture, they don't care which side is top or bottom. They just want you to draw these shapes here.
The shape is
Just the shape is important. The position, yeah. Continue? Yes? Okay. So notice that the voltage increases and decreases. This is actually a special type of voltage. This is called an alternating current. It's the current, the flow of the charge changes its direction. But a direct current, the direction is only one way. So up until today, when I drew, or when you drew a circuit diagram, you understand that the current is always moving in the same direction here. It doesn't change. But this new type of current, this is called a DC, this new type of current is called an AC, and its direction is like this, but then it changes and it goes backwards. So it doesn't have one direction, it keeps changing its direction backwards and forwards. So this is new. Previously it's been DC, now we're having a look at this thing called AC. In fact, that's what this is. This is AC, whereas your battery is DC. Okay. Have we got that? So like I was saying, this here is AC because that's how it was made, using the AC generator. So, yeah. So, Andy, I'm so tired, I completely forgot. You asked me, do you have a way to know which way the current is moving?
Yeah.
And I just completely forgot. Yes, you definitely do have a way. I was making a joke here. Do we have a handy way to figure out which way the current will flow? And the answer is yes. Using right hand. So, what you have here is motion, field, and current. So let me show you with the picture here. Motion, field, and current. So, right hand, yes. So, here, which way is the motion? Up or down? Up. So this is up, okay? Which way is the field? To the left or to the right?
Right.
To the right. So this is up, motion up, field right, current in. So this goes in. Now let's look here. Which way is motion? Motion is down. And which way is magnetic field? To the right. So which way is the current?
How is it going out?
Oh, north to south. So then the current will go to you.
Out.
Yeah, going out. So here it goes in and here it goes out. This is the right hand rule.
Right.
Yeah, so now you have, right. No, right. Yeah, for this one. So you have 3 rules altogether using your hands. You have the right hand grip rule. So if the current goes this way, the magnetic field goes this way. Then you have the left hand rule, force, magnet, current. And now you have the right hand rule, motion or force, like you said, force, field, current. I know, it's a lot to remember. So you have 3 hand rules now.
Do we have more later?
No, that's it, 3. So you have right hand grip rule, left hand rule, right hand rule. Charge in a magnetic field, and this is the AC generator. Yeah. Maybe you want to try and draw a beautiful hand. I know. Yes. Like this.
No.
Why is not this way, the current in your picture?
In my picture, yes?
No. Just the right hand.
Right hand, yeah?
Here, the picture says the third one is the current.
Correct.
But the position is different from this way and this way.
Put your hands like this. Make an L, cross. Like this, yeah.
So the current is pointing this way. Right?
Let me see your hands.
No,
Yes.
the picture.
Oh, the picture.
Yeah.
Okay. Yeah.
The current.
It's like this.
That one. The third one, the finger
Yeah.
is different from the last 2 fingers.
Oh, some people just use their hands like this and forget about these fingers. I keep my fingers together. That's all. Yeah. It doesn't matter. This or this is the same. Yeah?
But I mean, the position is different.
No, this is 90 degrees. It's
Don't
like,
care about this one. Ignore this one.
in this picture that you have, don't care about this, yeah.
Can you explain this?
Yeah, okay, one more time. One more time. Right, so watch carefully. What's this finger? Motion or force. So here, if you're turning the wheel, where's the force? Up or down? Up, yeah, because you want to, turn the wheel. So the force is up. So this must point up. Okay? Which way is the magnet? Magnet is going that way, from north to south. So this is the magnet. So this must go up, and this must go right. So you can see here, it's going in. Yeah.
This is going to the right?
This one?
Yeah.
To the right, yeah. North to south. Left to right. To the right. And this one up for motion.
Ours, the figure is different for yours.
Oh, it's not. Hang on, no, it's not. So it's the same. So look, hang on. Look.
That way.
Right. Thumb up. Agreed?
Yeah.
Yeah. Okay, and which way is the magnet? To the right.
Why?
From north to south. No. That way, yes. Yeah.
Wow.
So then the current goes in. Now, if I change the magnet, if I put the north on the right and the south on the left, then it's opposite way. Yeah?
What?
If I change the magnet,
No, I mean, what?
oh, then it's opposite. That comes out. Or
What
if
comes out?
the current. Or if I turn the wheel the other way, then I put my hand down. If I turn it the other way, push down.
So those up means it's turning to
No, what you need to do is here, imagine where is the force, up or down, to make it turn this way. So if you wanted to turn this way, the force must be up, because if the force was down, the wheel would turn the other way.
so turning this way is we are given.
Oh yes, this is given.
What is going right?
Okay.
What is we are going where?
Hang on. One more time.
Oh, I know.
What's this one for? Motion. Magnet. Current, yes. So the magnet, for example, is this finger. So that's going from left to right. The magnet's going this way. So I point this way. Now here, is the force up or is it down? When I turn the wheel, it's up, so I point up. So the current goes in.
The arrow is the force arrow.
Arrow is the current.
The orange arrow.
Like the force, yeah.
What do you mean going in?
Going in instead of going out. Goes in. Yes.
I hope my hand is easy.
Yeah.
Where is the current?
This is the current.
Current is
No, that's the magnet. That's the current. Yes?
but it looks the same way.
This?
The current and the
No, the magnet is going to the right and the current is going in.
out.
Yeah.
Okay.
Are you sure?
No. But okay.
Yeah, it's difficult, I know it's difficult.
Kill me.
Yes.
Now.
Is this okay? I'm not sure if it's okay.
How to use this theory
Okay, yeah. No, it's not for this picture. When you have a DC current and you put your thumb in the direction of the current, like this, there's a magnetic field going around
So
the
it's
current.
going up.
Well, it's going around like this. Yeah? Continue? Different.
DC and AC.
Oh, well, yeah, I suppose it's like this. Yeah. Okay, continue.
Yes.
Okay. So,
The left-hand rule and right-hand rule.
left-hand rule is when you want to know where the direction of the force is. The right-hand rule you use when you want to know what's the direction of the current. You don't get the same answer if you use one hand. You must use the left hand for finding the force, and you must use the right hand for finding the current. Yes?
Nothing.
Yes.
Right.
Yes. Maybe you need to practice.
Right-hand rule is for AC.
Yes. AC generator. And left-hand rule is for like DC motor, or for just any charge that moves in a magnetic field. You want to know where's the force, you can use the left hand. I know. Left hand is to find the force, right hand is to find the current. And in both cases, this is the force. This finger is the magnetic field, and the last finger is the current.
This is for left hand is for DC.
Yeah, left hand for DC,
Right hand
for AC. I know, it's a lot to remember. Yeah? Normally, when we look at the change in the magnetic flux, either the B changes or the A changes, but for our problems, not both. So this can become either A changing B, or for some problems it's B changing A. Most questions I do, I think the area stays the same and they change the magnetic density. Anyways, the only time we really have a look at when the area changes is when the area is swept out. So I need to draw that before we do a question. So here's an example. So for example, here's my copper, and here is north and here is south. Okay, and suppose I don't know, suppose at the beginning there's no magnet, and then all of a sudden I move a magnet over to it. So we have no magnet, and then we have a magnet. So here what's changing is the B. So the formula would be changing the B times the area. In this example, let's say we have a magnet, I don't know, and here I have something like a copper wire, and it's turning around. Here what's changing is it's so hard to draw, is the area. Here, I'll show you here. So look, imagine that this is north, and here this is south. So there's two ways to change this. You can either change the B, or you can change the A. So if you want to change the B, maybe you make this magnet stronger and weaker and stronger and weaker. So for example, maybe it's 5 Tesla, then it's 4 Tesla, then it's 5 Tesla. So you can change the B. Okay. If you want to change the A, then if here is the conductor, then maybe you could, change its shape. Or another way to do it is, if this is the conductor and you move it like this, then the shape it makes here as you move it, this is the change in the A. So my point is, when you want to change this, you can either change the B or you can change the A. Most of the questions in the exam, in fact nearly all of the questions in the exam, they do it this way by changing the B. So they would say like, there's no Tesla and then there's 5 Tesla. You know, or there's 5 Tesla and then there's no Tesla. That they change the B. They never change the A in the exam. I think only once maybe. I think it's better actually if I do some examples. So look, here's our first example. Write this one down. Okay. You got this example? I can do it now? Yes? Okay. So, firstly, how long is the pipe?
30 centimeters long, 5 centimeters long.
30 centimeters long and 5 centimeters wide. And then there's a wire wrapped how many times? 100 times. Wrapped around it. So it's 100 times. And then you have a magnet here. What's it? 1.5 Tesla. And the magnet, you move it in and out of the pipe.
Over time of 3 seconds.
Over 3 seconds. So what will happen as you're moving the magnet? You get a voltage, won't you? You get a voltage here. How much voltage? Let's calculate. So, the formula, you know, is minus, I won't worry about the minus, well, I'll put it in, minus n, change in the magnetic flux over the change in the time. Now, you know that flux equals BA. What's changing here, the B or the A? The B is changing, yeah. So I can take the A outside and just have change in B over the time. Now the question is, how does the B change? Well, at the beginning, there is no Tesla. And then you move this in, and then you have 1.5 Tesla. So the change is 1.5 Tesla. It goes from having 0 Tesla to 1.5 Tesla. So this is the change. Pi or squared, and then the change multiplied by 1.5 over 3. Okay, so what's that, please?
Maybe
0.098.
0.098.
And we don't need to worry about the minus. Oh. Yeah? Okay. Right. Here you go. One more example.
Question level or section
A or B? Yeah. For intake 1, the final exam was nice. Good, nice. The questions that the students got were like, you know, the past exam questions. They got one question on Kirchhoff. They got one question on, what was it? I think they got one question on projectiles. They got one question on waves. You know, they got, I think they got good questions. Maybe I'll show you sometime. No, I went on my holiday. I'll check the answers today.
Usually after more than 2 weeks to get their grades.
At least 2 weeks. At least 2 weeks.
And they get their grades by email?
Yes.
Wow.
More than 2 weeks though. Maybe like 4 weeks. Huh? Yes.
Enjoy your month.
Yes.
In our holiday, there's just only 1 month. Yeah. After 1 month, it's
Your exam, you probably won't get your results until like 1st of September maybe. Your exam is
so it means
your exam is the
closer date to
So
put
we
in
know
do we?
No, the university gets the result before you get the result.
Wow.
So as soon as the university gets the result, and then they confirm the offer, then we tell you the result. You are the last person to know.
And we will got the mail from university.
Or DIFC, yeah.
Before you go to university?
Yes, we will tell you which university to go to before you go to it. Yes.
Well, it's too late to prepare like visa or passport.
I know, the visa thing. But you still need to apply for your visa before you know if you got the grades, right?
Oh, yes, another question.
No.
No?
After we got offer, we can apply for visa.
Yeah.
Then we don't have time to apply visa.
Yeah, in Korea, like if you want to get a UK visa, then you need to do a lot of things, and we need to
Yeah.
prepare the 40,000,
Oh,
almost 40,000 euro for study visa,
Wow.
and then like a lot of things.
I know
Yeah.
I know usually it's okay, but I know sometimes at the UK it can be a bit of a rush to get the visa, but that's okay. You can talk to your tutor about what to do so you can do it on time. There is always enough time. I think one of the students told me before, I think it's different for each country, but sometimes it's quicker to get the visa for the UK in the embassy in Ireland. Sometimes it's quicker for the student to go back home to get the visa for the UK. I don't know what it is, but if you talk to your tutor, then they would maybe know if it's better for you to apply for the visa back in Korea, or if you have the Korean embassy in Dublin, yeah? Is there an embassy in Dublin for Korea? No, London.
Maybe take a little bit.
I don't
can.
You can ask them.
Yeah.
Where's your embassy? Your nearest embassy?
I don't know.
You don't know?
I don't have to go anywhere.
But what if you lose your passport?
It's not in job.
Okay, good. Okay, good. All right.
If you get a new GNID card,
Yes.
it's the same GNID number?
Oh, yes.
Oh, good, wonderful.
No change in GNID number.
I don't think so. You should be the same number.
Wonderful.
They write your number on your passport, don't they?
Yeah.
Yeah.
How long can you take your new GNID card when you go there and hospital?
It depends on the situation.
Usually how long?
Usually, no, it depends. Like, my wife's GNAB card is for 4 years.
No, I mean, when you go to the GNID
Yes.
and you talk to them, I need a new GNID card. And
Yes.
how long did it take to give you your new GNID card?
Oh, I don't know. I think it's going to be at least 5 hours, maybe.
5 hours.
Ah.
But that's okay.
Yeah.
Yeah, why?
Because we need to go to GNID
And
15th of
apply the reentry
this
visa.
month, and we worry about the time.
Don't
Okay.
worry. Everything will be okay. All right. Did you write this one down?
Yes.
A plane is taken off and heading towards Santa Claus at the North Pole. You know Santa? Yes. So, what you have in the picture here so this is Santa. Actually, Santa's red, so yeah, we'll give him. Santa here, and Santa is at the North Pole. So if you remember from my picture, when you have north and south, the magnet is actually like this, north and south. So anyway, the magnetic field heads to Santa. So the magnetic field is going this way. And here you have a plane on the ground. and the plane is taken off. And in fact, because the plane is made of metal, you actually get a current running through the plane. A very small voltage.
What is that?
This, the plane is taken off. Yeah. Now, if you look at the side, this blue line.
It means magnetic.
No, this is the current, and this one here is the magnetic field. So if you look at the side, here's Santa. Here's the plane, and the plane is heading up. Now, the magnet, which do we care about? The motion horizontally or the motion vertically? Yeah, vertically, because it's the one that's perpendicular. And in the question, I think I said the speed here is 600 meters per second. So what's happening here as the plane is moving, is the B changing?
No.
No. What actually is changing is the area. As the plane is heading up, you can imagine it's drawing a rectangle that's getting bigger. If it's going up at 600 meters per second, then in 1 second, how much of a rectangle will it make? Well, it will make a rectangle which is 600 meters high, and the width of it will be 68.5. So if you can try and imagine, look here, no wait, look. As the plane takes off, you can imagine we only care about the motion vertically, we don't care about the horizontal. So the plane, we only care about this motion. So as it moves, it makes an area. This is how much it makes in 1 second. So already you have change in area over change in time. Per second, you get 600 times 68.5. So when you want to calculate the voltage, it will be B times the change in the area over the time. The B is 0.07 millitesla. So what answer do we get, please? It should be very small.
2.877.
Yeah?
Yeah.
Milli?
No. 2.8.
Oh, that's bigger than I thought. 2.87 volts is what you get across the wings.
The area
Yeah.
of the right.
Here?
Where to that one.
Top, bottom, left, right.
Left.
Left, bottom. Here?
Yes.
Yeah.
This is the area.
Yeah, it's very hard for me to draw, but I'll try my best to draw it. So, as the plane takes off, we actually only care about the vertical. So it's changing its area with the magnetic field. We only care about the vertical because the horizontal is parallel to the magnet and there's no interaction in parallel, only in perpendicular. So the area is changing. The B is definitely not changing, it's constant, it's, you know, the Earth.
Just one area.
Yeah, I'm just trying to draw the picture to show you it's getting bigger. Yeah. Oh yeah, you want to show me the report. I don't have time now, I forgot about that. Can you email it to me so I can reply to you then, yeah? I thought you said you didn't type anything.
Difficult.
Okay, fine, whatever, you can send it to me. Yeah, can I go? Did you write this down? Yep, okay.
Only one area is okay. Or going up.
Yeah, it's per second.
Wow.
That's
Wow.
okay, it's okay, it's okay, it's okay.
Wow, for one day.
Now, you can't actually do number 1 because I didn't tell you something yet. So I'll do number 1 the next time. So if you can do 2, 3, 4 and 5.
Wow.
Only 2, 3, 4 and 5.
We finish at 5.
Exciting. Okay, can I close this?